Let's continue our discussion about predictive analytics by talking about how we estimate a model's generalization error and then how we choose between two or more competing models. So once again, when we're building a predictive model, all we're concerned about is that model's generalization error. We don't care how the model performs on the training data specifically. We already know the answers for those individuals. We want a model that makes accurate predictions on brand new individuals, ones that we haven't seen before. And that's what we mean by generalization. It generalizes to individuals the model's never seen. So that begs the question, if we have a data set and we know the answers to all the individuals in there, how do we go about estimating the generalization error of a model? How can we figure out how that model is going to be predicting on brand new individuals that haven't been seen before? Well, our main process is with k-fold cross-validation. And so in k-fold cross-validation, it's really best illustrated just with an example here. This is going to be our go-to procedure for kind of guessing what the generalization error of a model is going to be. So what we do is we take our training data and we split it up into k equally sized chunks. These four diagrams are illustrating when k is equal to 4, and here's how the procedure unfolds. Basically, the procedure happens in rounds, and in round 1, the very last fold, that last fourth of the data, is going to serve as the validation set. The model is going to be fit on the remaining 3/4 of the data. So the form of the model, coefficients, rules, whatever we're using here, the model is going to be fit on those 3/4 of the individuals in this part of the training data. And then once that's done, it's going to make predictions on the validation set. Now, this is a set of individuals the model hadn't seen when it was being built with those 3/4 of the data points. And so for all intents and purposes, it's like the individuals here are brand new. So we make predictions, we get an estimate of the generalization error, and then we move on to the next round. In round 2, the identity of that validation set rotates. So round 1, it was the very last chunk. In round 2, it's the second to last chunk, but same deal here. The model is fit using the individuals in the remaining bits of the training sample. And then the model makes predictions on the individuals in that validation set. So we get a second estimate of the model's error on brand new individuals. And then we continue through round 3 and round 4 until every one of these chunks has had a chance to serve as the validation set, that set of new individuals that the model hadn't seen before. And the overall estimate of the generalization error is just the average of these 4. So we can choose the value of k. Normally we do 5-fold cross-validation, sometimes 10-fold cross-validation. And in fact, we can repeat the whole procedure, do repeated k-fold cross-validation by randomly reassigning where the individuals land in terms of which of these chunks they live in. But for the most part, in the 479, we'll just stick with 5-fold cross-validation. So we'll take our training set, split it up into 5 equal chunks, fit the model on 4 of the 5 chunks, make predictions on the remaining 1, use that as a guess for how well the model generalizes to new individuals, average together those 5 different guesses, and call it a day. That's going to be our best guess for the model's generalization error. Now, when we go and do predictive modeling, since we don't know what's going to work ahead of time, we're going to fit a whole bunch of different models and a whole bunch of different ways of building them. And so we're going to have to decide, all right, which is going to be our favorite model. And here's kind of the surprising thing. We don't actually have to be that strict in choosing the model that had the lowest estimated generalization error. And I think this diagram shows us everything we need to know to understand why. So in this case, this is an example where a bunch of different models were fit to predict an individual's BMI index based on some physical measurements like their weight, their wrist circumference, their chest circumference, abdomen circumference, etc. And so every single dot here represents a model with a different number of predictors, different number of interactions, raised to different numbers of powers, but each model is a dot. And on the horizontal axis, we have the estimated generalization error of each one of these models as found through 5-fold cross-validation. So there looks like there's a pretty big difference in quality of these models. The estimated generalization error is anywhere from around 3.8 percentage points up to 4.6 percentage points. But here's what's interesting. If we go and actually look at the actual generalization error on the holdout sample, well, each model's actual generalization error on the holdout is plotted on the vertical axis here. And what we find is two things. Number one, this diagonal line represents where both the values match up exactly. The estimated generalization error matches up exactly with what it was on that holdout sample. Now, that's never really going to be the case, but what we see here is that there's a trend. Very often, the estimated generalization error is overly optimistic. We find that the actual generalization error is typically above this line. So in this case, well, we estimate a generalization error of 4.2 percentage points, but guess what? This model actually ended up making an error of something like 4.6 percentage points on the holdout. Some of the models actually beat estimates, but the vast majority of models are overly optimistic in how well they generalize to new individuals. And that's pretty typical no matter what the context here. So lesson number one, our estimated generalization errors are typically pretty optimistic. In actuality, on real data, we'll probably do a little bit worse. We expect that. But number two is that the model with the lowest estimated generalization error, this guy right here on the very far left, is by no means the model that ended up actually doing the best on the holdout sample. So any dot that's below this far left dot is one that actually did better on that holdout sample than the one with the lowest estimated generalization error. And so we find that there's no shortage of those, indicating that, hey, after we go through and estimate the generalization errors of all of our models, we're going to have a choice. We're not going to feel compelled to go with the one with the lowest estimate. Now, we can do that, nothing wrong with that, but we do have a choice. And what kind of captures how we think about this choice is the one standard deviation rule. So the one standard deviation rule is one of these most important things to keep in mind when doing predictive analytics. After we've auditioned our full set of models, we're going to have a choice of what we can choose for the model that we want to deploy. And here's the philosophy here. If we go and estimate the generalization errors with k-fold cross-validation, we can compare two different models and their estimated generalization terms using their standard deviations as a yardstick. So the statement of the one standard deviation rule is if when we're comparing two different models, we find their estimated generalization errors are within one standard deviation of each other, there's really no compelling statistical reason to go for one versus the other. There's really a bona fide choice here, and you can feel free to choose whichever one you would like. Maybe you really want to do the simpler one. It had a slightly higher error. This says it's okay to do as long as those two errors are within one standard deviation. So what does that one standard deviation actually refer to? Well, it ties back into the values that we got out during k-fold cross-validation. So if we did 10-fold cross-validation, well, we would get 10 estimates of the generalization errors. That training data would have been split into 10 equally sized chunks, and each one of those 10 chunks would have had a chance to serve as the validation set. And so if we were to look at the distribution of those 10 estimates of the generalization error, we'd find a little bit of variety. And if we just looked at the standard deviation of those 10, that's what that standard deviation is referring to. So as we work through the carrot package to do our model fitting and model evaluation, we'll tell it to do some 5-fold cross-validation most of the time. The standard deviation of those 5 estimates serves as the standard deviation that we'll use in the one standard deviation rule. Carrot will report that back for us. And we're going to know that if we find two models whose estimated generalization errors are within one standard deviation of each other, then it's a choice. It's a toss-up. The data doesn't specifically say, hey, you got to go with this versus the other. We're going to have a choice there. So let's talk about our overall strategy for choosing a predictive model. One of the most important slides in all of predictive analytics. So to choose a predictive model, number one is that we need to take all the data that we've collected and really split it into a training sample and a holdout sample. We need to set aside a small bit of data, this holdout sample, to serve as a sanity check to make sure that our model's not overfit. So we'll split the data into two, a training sample and a holdout sample. We'll set aside that holdout sample to the very end. And then we're just going to go ham on that training sample. We're going to fit hundreds, thousands of different predictive models. We'll estimate the generalization errors of each one of them. And then we're going to make a choice. We're going to choose our favorite. Either the model with the overall lowest estimated generalization error, or maybe one that's acceptable in terms of the one standard deviation rule. Maybe one that's maybe a little bit easier to interpret or explain to your boss. Maybe one that's relatively simple. We like simple in business analytics. Caret, by default, is always going to be choosing the one with the lowest estimate, but we know we're not compelled to do that. So once we've selected our model, well, we'll fit that model to the entirety of the training data, and then look to see how well it actually generalizes to the holdout sample. We'll get that generalization error on the holdout sample, and those two better match up pretty closely. The estimated error should be pretty darn close to the error that it actually is on the holdout sample, because if it's not, if the estimated generalization error is a lot lower than what we end up finding on the holdout sample, that's indicating our model is overfit. Essentially, we've memorized too many quirks and features unique to the individuals in the training data. It's not existing in the data in general on the holdout sample, and so we should go back to the drawing board. So once we make those predictions on the holdout sample, we'll know if we have a good model, one that's not overfit, when we compare those two. I'm just going to arbitrarily throw out the guideline that the error on the holdout sample needs to be within 10%, no more than 10% bigger than that estimated generalization error. That's going to be my personal threshold for what I would consider an overfit model, a model whose error on the holdout is larger than 10%, what we expected it to be during that k-fold cross-validation procedure. And there we go. Now, one thing to keep in mind, and because we're all really curious, one thing I like doing is saying, okay, well, what if I had chosen a different model? I might actually go and find different models' errors on the holdout sample, and that's fine out of curiosity's sake, but the key thing is that when we're doing this procedure for real, we're really only using that holdout sample once, and just as a sanity check for that final selected model after we've auditioned every single one of them. If, out of curiosity, and we'll very often do this, you make predictions from a different model on the holdout sample and you find that it actually did better on the holdout sample, don't switch models. So the reason why is that this holdout sample is designed to be only used once. If we use it more than once, everything that we're kind of learning from it goes out the window just a little bit. Out of curiosity, sure, it's okay to see how other models would have done, but that's not going to be a definitive push to switching towards another model. I'll recommend to stick with your originally picked model. That holdout sample might have been just a hard one for the model that we picked, and that other model that you're checking, it might have had an easy time with it. You never really know. So stick with that model you selected. All right, so this sounds like a lot of work. Now the nice thing is that Caret will do almost all of this for us very, very quickly. But there's a good reason why we actually have to go through and split this training and holdout data, audition lots of different models. There's this remarkably fun theorem called the no free lunch theorem that essentially says no matter what kind of model we like, maybe you have a pet model, it's not always going to be the right choice. So the no free lunch theorem guarantees us that there's never going to be one correct way to do predictive modeling. So right now, maybe deep learning is all the rage, reinforcement learning, neural networks, etc. That might be great on a huge number of problems, but the no free lunch theorem says, hey, there's still going to be a chance for these other models to shine. It's not going to be the right choice for every problem out there. So every model that you learned about in 474 and 320, even down to a simple linear regression, is sometimes going to be the right choice. We're just not going to know what that choice is ahead of time. That's correct. So we just audition everything. We try everything out and see what seems to be tuned, for whatever reason, for the particular problem that we have in mind. So there we go. That's how we do predictive analytics. In the last little video, we will talk about how we evaluate different models, root mean squared error, accuracy, AUC, naive model, etc.